recording. This is Tech Math 2. And we're in section 3-1. Maybe we're in section 3-1. Oh. Now we're in section 3-1. Much better. All right, well, if we have an angle, this is part of our English training again. If we have some angle, then we have an initial side, which means that's where we start. We have an initial side of the angle. And then we have the angle itself. We're going to call it theta for the lack of any other good thing to call it. And then we have a terminal side. So that's where I end. Normally we're going to look at, wow, that's pretty exciting. Normally we're going to look at an XY plane and say that the terminal side is going to be on the x-axis at the 0 position, and the terminal side is going to be somewhere going around. But we don't necessarily have to draw it that way. It could be any place at all. And then we have the issue of a circle. So if we have a circle, we'll start with some angle. We have a center. Wow, touchy, isn't it? I'm going to push a button, see if that makes any difference. Normally button pushing helps. Yeah, that helps. What was happening before is the screen is touch, and the screen can be used by the pen, and the touch thing was on it every time I touched it, it did something. Anyway, so we have a circle, and we have some initial side, and we come over to some terminal side, and we have some theta. And if we go all the way around to the other side, and we come back to where we are, we'll have gone 360 degrees. And the reason we go 360 degrees is because the ancient Babylonians gave us a numbering system with 60 different numbers. That's why we do. That's why there's 60 seconds in a minute, 60 minutes an hour, because the Babylonians 4,000 years ago did that to us. So that was just very nice of them. And then 1 degree turns out to be 1/360th of the circle of the complete rotation. And then we don't necessarily have to have degrees. We can have degrees have minutes. So 1 degree has 60 minutes. And then 1 minute, if I could make a minute, 1 minute has 60 seconds. So again, the ancient Babylonians divided their circle into 60 parts, but they divided those 360 parts in degrees, but each of those degrees have 60 parts, and we call them minutes, and each of those have 60 parts, and we call them seconds. And so a second of angle, so if I was going to draw a second of an angle, it'd be sort of like that, right? It'd be kind of small. But as you go further and further away, that second becomes wider and wider as you get further and further away. So when you take 1 second of arc and you go and you look at out in space at where there is absolutely nothing in that direction, and you take the Hubble spacecraft and you point it in that direction, you see galaxy upon galaxy upon galaxy. And it would be nice if I spelled arc right for the, that'd be good too, arc. Okay, that's good. So now the issue is, how do we get, so some wonderful person tells us 3.5 degrees, and we want to change that to minutes and seconds. What are we going to do? Well, we'd say, well, that'd be 3 degrees and then half a degree would be 30 30 minutes. Yeah, that's what we would do. What if we had 3.4597 degrees? What would we do then? Well, we'd write down the 3 degrees, and then we'd say, okay, what do I have left over? I have 0.4597. I'm going to multiply that times 60. Why am I multiplying by 60 for? Well, because these are degrees, and these are minutes per degree, so now I'm going to get minutes out of that when I do that. Okay, so if my calculator was on point, I'm almost there. 0.4597 times 60. And I get 27.582 minutes. So I can say that this is going to be 27 minutes. And then I take the fractional part, 582, and I multiply that by 60 again. 0.582 times 60. And I get 34.92 seconds, and I'd probably round that off to 35 seconds. Okay, so that's how I would do that. I would go and take my degree, take the fractional part of the degree, multiply it by 60 to get the whole minutes, take the fractional part of the minutes, multiply by 60 again, and get the fractional, the part that are seconds. So that's how I would go and change from degrees to degrees, minutes, seconds. Now, if I had my older calculator on, the TI-36 that's not the Pro, it had a button that did that directly. And it might still be in here, but I certainly don't see it. It's not in the convert, and it's not in the math, and it's not in the complex. So I'm not sure where they put it. But we used to be able to go from degree, minutes, seconds the other way. Okay, well, let's go the other way. Let's say I've got 34, we'll call it 39. 39 degrees, 37 minutes, 59.2 seconds. And if I could spell minutes, then that'd be good too. Okay, so I want to change that to a decimal degree. All right, so that'd be 39 plus 37 divided by 60 plus 59.2 divided by 60 squared. And that's what I would put in my calculator. 39 plus 37 divided by 60 plus 59.2 divided by 60 squared, and looks like I got 39.6331 repeating. But then I'd have to ask myself, how many significant digits do I have? And I'd say, well, you know, seconds, portions of a second, that's pretty small. So I'd probably keep 5 of them, 39.633. And I might even keep one of the ones, who knows. I might want to do that. I'd go the other way and see if this gives me that, and if it didn't, then I'd have to keep more of these in order to have enough significant digits to go by. Okay. We have one other thing to consider. It's not until chapter 10, but in chapter 10 we get to radians. And your calculator can be in degree or in radians. So when you go to mode, you can be degree, radians, and gradians on top. Never be in gradians. The only time you'd want to be there is if you're a civil engineer. For an electronics person, we're either in degrees or we're in radians. Those are our two choices. And we can do all our calculators in radians. But what happens is, decides to do something else. All right, so what happens is I've got a circle. The circle's got some radius r. If I take that radius r and wrap it around the circle, then the measure that I have there, that angle, would be 1 radian. So when I go all the way around the entire circle, I have 2 pi radians, because the circumference of a circle is pi d, which is 2 pi r. Okay, so that's cool. Okay, so now we're on page 119. And we get to worry about sines and cosines and things like that. So the Greeks did this to us 2,005 years ago. And they decided that the sine, if I have some triangle, and the triangle's a right triangle, then it's going to have some angle A, B, C, some side A, some side C, some side B. And I'm going to be consistent with the author, I'll put the B in a different spot, and the C, and then C, B, side C. So I'm using lowercase for measures of the sides and uppercase for angles. And if I ask myself, what is the sine of A? And I'm going to have side opposite. Side opposite, also known as A, divided by the hypotenuse. And again, why did we ever get that word from? Well, the Greeks did it to us, so we'll just blame them. Divided by C. Cosine A, side adjacent, which is going to be the B guy, divided by the hypotenuse. And then we have tangent A, side opposite, side adjacent. A over B. Now, if I want the sine of B, then the side opposite would be B, and the hypotenuse would be C. So I'd have to call it something different. And then just to make our lives better, we have cotangents, and we have cosecants, and we have secants. And our cotangent is going to be 1 over tangent, and our cosecant is going to be 1 over sine, and our secant is going to be 1 over cosine. And why they did that to us, I don't know. That doesn't make any sense at all, doing it that way. But we've been doing it that way for several thousands of years, so that's the way we have to do it. And we'd have to throw in an angle too, right? So cotangent of A, cosecant, secant, tangent A, tangent, blah, blah, blah. Okay, any problem with that? And Pythagorean theorem says that A squared plus B squared is equal to C squared. Just for the heck of it, we'll throw that in. Okay. Now, with all those things, clearly we have 3 more chapters to do on sines and cosines, so there's obviously a lot more to go on. And, so we'll worry about that later. We'll look at problem number 1. I'm looking at number 1, and it wants me to draw a use a protractor. Anybody got a protractor? Well, I do. How come you guys don't have a protractor? See, let's see if I can find my protractor. Essentials. Yeah, this is an essential thing, all right. And there's mathematics and shapes and measures. Yeah, shapes and measures. Angles. Angles. Pictures, interactive, backgrounds. All right, I'll look at the interactive guy. Oh, there's a protractor. There we go. I knew I could have a protractor. All right. So now I have a protractor. Even though you don't have a protractor, I get to have a protractor. All right, there we go. And now we want to draw an angle that's 35 degrees. Okay, well, I'd go from there and draw an angle like that. And then where's 35? There's 35, like that. There we go, 35 degrees with a protractor, exactly as the problem told me to do it. All right. Could you do it without a protractor? No, of course not. It tells you to do it with one, so you'd have to do it with it. Okay, well, that solves that problem. All right. We'll go to number 12 next. We want to know how many minutes do I have? All right, so number 12, and I have 0.7 degrees. All right, so I want to know how many minutes. All right, so 0.7 times 60. Dimensional analysis, 7 degrees, minutes per degree. The degrees go away. All I have is minutes left. Oh, wait a minute. 7 times 6. 42? Yeah. So I have 42 minutes. All right, well, that was okay. Number 16. I'm just getting warmed up for the rooms. I have 120 degrees, 11 minutes, and I want to change to decimal degrees. Each angle 2 degrees. Okay, so I've got 120 plus 11 divided by 60. And I'd probably just do that in my head because, you know, it's so simple. I can't turn on my calculator here, so I'd probably have it done if I did it in my head. 11 divided by 60. Yes, that's exactly what I thought it was. 128.183 repeating. And then I'd say, well, probably don't have that many significant digits. But I'd leave it that way anyway, just for the heck of it. Okay, number 20. Anybody know what number that was? That was 16. 16. Oh, much better. Number 20. I've got 7 2/5 degrees. So that would be 7 degrees. And then I go 2/5 times 60. And 24. 24 minutes. Okay, good enough. We'll look at 28 next. I got 29 degrees, 29.608 degrees, and I want to go to degrees, minutes, seconds. Okay, so 29 degrees. Then I take 0.608 times 60. 0.608 times 60. And I get 36.48 minutes. All right, so I write up here 36. minutes, and then I go 0.48 times 60. 0.48 times 60, and I'd have 28.8 seconds. And then I'd ask myself, do I really care about the fraction of a second? And I'd say, probably not. 29 seconds. Okay. So use figure. I see the figure. Okay, so I got a figure. Looks like that. I got an angle there. A, B, C, B, A, C. Okay, so I got my figure made, and I want number 30. I want this the side opposite to B. B? Really? Is that all we wanted? Look at 38. 38. What is the side adjacent to, what is the angle adjacent to side B? Well, they probably don't mean the 90-degree guy, so they're probably asking for A. That would be my guess. Okay. So we did 30, we did 38. Now we're going to do 48. Find the length of the third side to 3 significant digits. So how many digits are we going to have? 3. Okay, so 208 squared is equal to 155 squared plus A squared. Alright, so A is going to be square root of, is it plus or minus square root of? 208 squared minus 155 squared. No, it's not plus or minus, even though it would be plus or minus, but it's not plus or minus because a negative length doesn't make any sense in figuring out what an angle is. Okay, so square root of 208 squared minus 155 squared equals. Okay, so my glorious calculator says 138.7047,223, but my final answer is supposed to be to 3 significant digits, so my final answer is going to be 139. Do I have units? Yes, I do. I have units. If I don't put down the units, is the problem wrong? Yes, it is wrong. Right, so if I'm given units, I'm going to have units in my final answer. I don't have much of a choice there. Okay, number 54. Find 6 trigonometric ratios to 3 significant digits. Well, at least we have 15 minutes to do it. I mean, what more do we want? Okay, so that's what we're going to do. Okay, so we know that B is 239, and we know that C is 307, so we need to find A. So A is going to be the square root of 307 squared minus 239 squared. Now, who said it was a right triangle? Where in the problem that says this is a right triangle? Nowhere. But in this section of the book, do we have anything but a right triangle? No. So we have to assume we have a right triangle because the problem wouldn't make any sense any other way. Square root of 307 squared minus 239 squared. So I got 192.686. Because A is not a something that I'm worried about significant digits on because it's not a final answer, I'm going to keep all 6 of those digits. All right, now that I know that, I'm going to write down, I'm going to make a picture. Okay, so here's a picture. A, B, C, C, B, A. And I want sine, find sine, which one? Angle A. Okay, so sine A. Opposite, little a, 192.686 divided by the hypotenuse, 307. Cosine A. Cosine A. B, the side adjacent, divided by 307. Tangent A. Tangent A. Side opposite divided by adjacent. Okay, so those are numbers we're going to want, and we're going to go and say the cosecant of A is equal to something. The secant of A is equal to something, and the cotangent, if I can spell cotangent of A is equal to something, because once I get the sign, all I have to do is go 1 over that guy and I get the other guy, so I'm just going to write him down. Okay, so 192.686 divided by 307. And I want it to 3 significant digits because it's telling me it wants 3 significant digits. Okay, that's good. So I've got 0.028, 628. 1 divided by my answer, and I've got 1.59. Okay, I've got 239 divided by 307. I've got 0.778, and because the 8 is even, I'm not going to round it up. 1 divided by my answer, I have about 1.28. Tangent 192.686 divided by 239. Oh, and go with 0.806. And then I'm going to go 1 divided by my answer, and I'm going to get 1.24. Okay, so that's what I'm going to do. We're going to do 62. Yeah, I think we'll do 62 next. Find 6 trigonometric ratios of the angle B using triangle ABCD and B using angle BFG in the figure below. Round off to 3 significant digits. Okay, so the figure below is 3.15. I see it. Okay. Using angle B, using BAC. BAC. Okay. Okay, so I have 12 answers to the problem. Okay, so I got the A part of the problem, which says I've got this triangle B, A, C. So I got this triangle that looks like that, and I've got a 9, and I've got a 6, B, C, A. I've got to find the hypotenuse. Square root of 9 squared plus 6 squared. Ready to go. All right, well, we'll go with that. 3, the square root of 13. 3, the square root of 13. Okay, so we'll do that. All right, so we want sine B. Okay, sine B. So that'd be 6 divided by 3, the square root of 13. And then we want cosine B, 9 divided by 3, the square root of 13. Tangent B, 6 over 9. And then we're going to go with cosecant B, secant B, cotangent B. And then we're going to take our calculator and we're going to take it out of math type and put it into classic. And in classic, it's not going to give me that square root guy in my answer. It's going to give me the decimal answer that I'm looking for because I want to round off the 3 significant digits. Or do I?
If you hit the button right before the enter button.
You could. Yeah, above the enter button, yes, you could. You could use that too. Yes, I want 3 significant digits. So I could have kept it in math type and then told it to convert to a decimal is what Nate is telling me. Yeah, I could do that too. I'm skipping a step and putting it in classic. Okay, so 6 divided by 3, also known as 2, divided by the square root of 13. And I have 0.555. Well, that's better than 666, right? 1 divided by answer 1.80. Okay, 9 divided by 3, also known as 3, divided by the square root of 13. 0.832. 1 divided by the answer 1.20. 6 divided by 9. 0.667. Okay, so that's good. 1 divided by the answer 1.5. Okay, so the A part is done. Now we get to do the B part. Okay, so the B part wants me to use angle triangle BGF. Okay, so I'm going to use triangle BFG. Now, I'm looking at BFG, and I'm looking at ABC, and I'm saying these guys are similar triangles. Similar triangles are going to have the same angles. If they're going to have the same angles, they're going to have the same trigonometric answers to 3 significant digits. So, that being the case, I'm going to move up here like that, and I'm going to change my color and say sine of B is 0.555, and cosecant of B is 1.80, and the cotangent of B is 0.823. The secant of B 1.20. And the tangent of B 0.667, and the cotangent of B 1.5. Okay, anybody object to that? We should check one, right? Just to make sure. All right, so we'll go back to the tangent of B has to be the opposite side 8/12. If 8/12 isn't 0.667, then I am totally completely wrong. If it is, then we'll assume and I am right. It's 2/3. I have 2/3 whether I have 8/9 or I have 6/9 is 2/3, and 8/12 is also 2/3. Okay. One last problem, number 64. Given that A is this and the cosine of A is that, compute the remaining 4 trigonometric functions of A. Okay, so we want we'll go with something easy. We'll go with cosecant. Cosecant of A, 1/sine A, which is given. All right, 1/sine A. 0.8381 divided by 0.8387. And 1.91923, 4 significant digits, 2. All right. And then we want the secant of A, which is 1 over the cosine. 1 divided by 0.5446. 1.836. 1.836. Then I want the tangent of A, which is going to be sine A over cosine A. Do we know that? Did the author tell us that? I don't know if the author ever told us that. I wonder if it's true. Okay. 0.8387 divided by 0.5446. Boom. 1.540. 1 divided by my answer, cotangent. 0.6493. Okay, good enough?